Hi everyone, today I'm going to walk through some basics of probability with applications in R. So just a little bit of notation to get us started. So there's a lot of different notation and it can look kind of tricky, but when you learn what it means, it's not too bad. So you can denote an event, so just something that happens, like it will rain today, that's an event, and we can assign that a probability. So say that's our event, we call it A, and then the probability of it raining today is, say you think or that it's 0.1. And then you have these operations with, if you have two events, so say A is it's going to rain and B is it's going to hail. So you have the union, which is the probability that it rains, or the probability that it hails, or both. So that's just the combination of both of those. The intersection is the probability that they both happen, and not just one by themselves. And then the complement, which is this little A to the C looking thing, that's the opposite of event A. So if you think the probability is 0.15 that it rains, that means the complement is 0.85. And that's usually really helpful because we sometimes don't know every other possibility, or we don't know the probabilities, but if we know one thing, we know the opposite probability, so to speak. And then the conditional probability, this little bar here, means, if it's hailing, what is the probability that it's raining? So it influences the first event. And not getting too much into these, just some basic notation to get us started. And there are some axioms. These are sort of the laws of probability, and I only have the first two. There's a third one, and there's different sort of rules, and you can get really in depth, but we'll just look at the basics. So a probability has to be between 0 and 1. That's what this little thing means. This little in, it just means, the probability of A has to be in this range from 0 to 1. And then the sum of all of these probabilities in a space has to sum to 1. So, if you have probability of A, that 0.15 probability that it rains, and a 0.85 probability it doesn't rain, that has to sum to 1. That's just a rule of probability. So either it happens or it doesn't. Those are the only options. So we'll do a little bit of basic setup, and you can always find a probability book and do problems all day, but just some setup. So if you have a fair dice, what's the probability you roll a 6? And you probably already know it's just 1/6. You have 6 different choices, and if it's fair, you just have a 1/6 chance you get that specific number. So then our sample space here is just what are the possible outcomes. List everything out. So we have 1, 2, 3, 4, 5, 6, and sometimes this is pretty difficult to map out, but it helps us to structure our code that we'll write later. So the probability that you roll anything other than a 6, and this is where that little trick comes up, where, so say the event B is we roll anything that's not a 6. That's equal to 1 minus the probability of the opposite. So we do 1 minus 0.166 to find everything other than a 6. So just a quick little trick there. And then we can do a lot of this by hand, but it gets really tedious, and it involves a lot of calculations and sums and things that's kind of easy to make mistakes. So we'll do it in R, and we'll write code to do this. So fortunately, the distribution functions, and there are a bunch of different distributions, and we're not going to go through all of them, but they follow pretty much the same format in R, and they're loaded in with the base stats package. So R binom is the binomial distribution, and it's the random sample part of it. So we can actually run this and look over here on the right, and we have these really helpful 4 family of functions that operate very similarly. They do different things. So this is like for percentiles, this is for quantiles, this is for the density, and this is for drawing samples, the R binom. And this is really nice because every other distribution, it's exactly the same sort of format. So if you want to draw from a normal, you just do R norm. So it's really nice, easy to remember. So say we want to draw some samples, and this is always really useful to try to simulate things. So when we say simulations, it's like, if you don't want to flip a coin 20 times, you don't have a coin, you can set this up and try to do it with quick little simulation. So n is the number of trials, and this is basically just straight from over here. The size is the options of the outcome, so it's the sample space essentially, and then the probability of success is p right here. So we know that because it's 0.5, the probability of failure is also 0.5. So we run this, and we see these are our outcomes. So say the ones are heads and the zeros are tails. Great. And we can keep running this and get different results every single time. You see how they're changing? And, okay, say someone asks you, like, how many heads did you get out of 20 flips? You run this and sum it up, and you've done a quick simulation. It's very easy. So, and then a little bit more math. So the example we looked at earlier, the Bernoulli distribution, is a special case of the binomial. And that is the binomial, you have multiple outcomes. And the Bernoulli is just you have like a 0-1 outcome and you're running a single trial. So again, a little bit of math is a little bit tricky at first, but this n choose x, this is the choose notation, so it's a combination. So if you roll, if you flip 10 coins and any 3 of them, it doesn't matter which 3, so say the first one, the 5th one, and the 7th one are 3, or the 2nd, the 6th, and the 5th, that denotes that it doesn't matter which ones are successes. And then p is the probability, q is 1 minus p, and then we raise to these powers. So, say we have like, and it's always easy for me to kind of write it out and just to look at it. So say your friend gives you an example and says, calculate the probability that of 10 flips you get exactly 3 heads. So we do 10 and 3, and then we just plug those numbers in up here. So we raise to these powers, and we know, say it's a fair coin, and we plug 0.5 in here, so for probability of head and tails, and then this is how we denote this with mathematical notation. So just probability that a equals 3, so we get 3 heads. So we use this D binom here, and this calculates, this is what we call a density. So it's just the density at this number, and we have 10 trials and a probability of 0.5. We can run this, and we see that it's 0.11. So you could do this by hand. I mean, it's not too computationally tedious, but when you get more and more complex examples, it can take forever to do by hand. And then, like I was saying, there are tons and tons of distributions, and you can do a lot of reading on them and look at the math behind a lot of these. But some basic ones, the binomial, the Poisson, they all have their normal, Bernoulli, they all have their sort of specific applications. But in R, they're all sort of use the same syntax, which is really nice. And same thing here. You can just run this again to read more about it. And then here's a great free resource with a guide on some of the math behind probability, and good luck programming.